Hey, this is Mr. Aiden. This is AP Chemistry 2013 AP exam practice problem number 6. So we are in our preparation for the 2020 AP Chemistry exam, and we're going to be going through the 2013 AP Chem exam practice problem number 6. Remember, when you're done doing this problem and you're done looking at this video, you're going to score yourself. You're going to put your score in where it says put your daily AP Chem test score here each day. And so you're going to be grading yourself. So let's get to this problem and see what it looks like. You take a look. We have compound number 1, compound number 2 with the same empirical formula, but it's going to have a different structural formula. You can see one of these chemical formulas, the first one, it says it's slightly soluble in water. What does that mean if it's slightly soluble in water? That probably means it has very weak intermolecular forces. Something maybe like LDF, something maybe like some dipole-dipole forces. But it is not going to be very soluble in water. You take a look at this second compound, it's very soluble in water. High boiling point, that's probably going to have hydrogen bonding attractions in there. Okay? And so even just taking a look at what we know about the boiling points, the solubility in water, we're going to take a look at each one of these things, and we already know what they're probably going to ask. Question number A1 says complete the Lewis dot structure for box in box X. And so remember, hydrogens always have single bonds here. The carbon is trying to get an octet, so that's 8 valence electrons around those carbons. You remember oxygen has 6 valence electrons, which means there's going to be 2 left over, and you need those 2 sets of unshared pairs, which makes that a bent side of this molecule right there, an sp3 hybridized. And so we're going to get 1 point for the correct Lewis dot structure for that, Lewis electron dot diagram. If you did not include those dots, you do not get that point. And then it says in box Y, draw a Lewis electron dot diagram for the second one, for something that would be for another way to look at this C2H6O. And so of course we're going to take a look at something like this. We have our CH3 on this side, we have our CH3 on this side, but we're going to have an O in the middle, and so this is going to be an isomer, and that O is going to have an unshared pair. And so this is worth 1 point as well. And so this is, you can see this O will be bent in the middle, but it's not bonded to a hydrogen, so there is no hydrogen bonding interactions going on. And then you can see B says, on the basis of the complete Lewis electron dot diagrams you drew in part A, identify which one and justify your answer in terms of intermolecular forces. And so you can see right here, and I'm going to draw this maybe in the green color right here, is right here on the end, this is going to be compound 2. Okay, compound 2. And why is it going to be compound 2 is this OH is going to give about some hydrogen bonding attractions. Okay, there are some London dispersion forces. Obviously, there's London dispersion forces within this molecule, but that OH, that COH, is going to give you hydrogen bonding attractions, which will be very soluble in water. Okay, that is worth 1 point for that kind of rationale. The second point is coming from this box Y, and this box Y, this will be compound, box Y will be compound 1. And why will it be compound 1 is it simply just has some dipole-to-dipole forces. And of course it has London dispersion forces going on. But this COC, this COC bond is just going to be dipole-to-dipole interactions. So that is worth 1 point as well. So you can see A is worth 1 point for completing this Lewis electron dot diagram. B, A2 is worth 1 point, and then B is worth 2 points for identifying compound 2 with a justification, compound 1 with a justification. So we're already through 4 points of our 9-point problem. So it brings us to the second part of this problem, and we have two different molecules here. We have dichloromethane and we have carbon tetrachloride. You can see the boiling points of dichloromethane is lower than the boiling point of carbon tetrachloride. The vapor pressure is higher, and so those correspond with each other. So C asks, dichloromethane has a greater solubility in water. So again, we're looking at interactions with that hydrogen bonding attractions of water. And we want to make sure we identify each. So you can see this dichloromethane has greater solubility. So this dichloromethane, this CCl2H2, that has some dipole to dipole interactions, some polar interactions with the water's polar interactions. Okay, and so that is worth 1 point for stating that. 1 point for stating that. Then you get a second point for talking about the carbon tetrachloride, the CCl4. The carbon tetrachloride is only going to be London dispersion forces, which will not interact with the hydrogen bonding, the polar forces, the polar interactions of the water, and that is worth 1 point as well. So you can see C is worth 2 points. 1 point for talking about the dichloromethane, how those polar interactions will interact with the polar interactions of the water, and then the dichloromethane not interacting, those London dispersion forces not interacting with the hydrogen bonding attractions. Okay, so the C was worth 2 points total. Then D is asking to explain this higher vapor pressure, and vapor pressure goes along with boiling point. Vapor pressure is the pressure to be a gas. You can see dichloromethane has a greater pressure to be a gas. So the greater the vapor pressure, the weaker the intermolecular forces. And you can see dichloromethane, this CCl2H2, we said he's got pretty strong interactions, doesn't he? He's got dipole-dipole, and he's got London dispersion forces. The carbon tetrachloride only has the London dispersion forces. So why would the London dispersion forces of carbon tetrachloride be stronger? And it is because we have more London dispersion forces. We have a greater, what the term we like to use, polarizability. Polarizability. And if it has greater polarizability, it will have a lower vapor pressure and a higher boiling point for that. And so that was worth 2 points. 1 point for each discussion of the intermolecular forces of the dichloromethane and the carbon tetrachloride. So again, C and D were worth 2 points each, and we're closing in on our final point here. Okay, it's only worth 1 point. We have formaldehyde here, and we have to show a hydrogen bonding interaction. So if you remember, this side of the molecule over here only has London dispersion forces. It's this side of the molecule that has some dipole-dipole forces that will interact with the water. So the O of this CO, remember, that has a slightly negative charge, and so that's going to interact with the positive charge of the water. And so you can see water has H2O, like that bent molecule, and I'm going to draw this hydrogen bond in green right there. And there is your hydrogen bond, or what we call hydrogen bonding attraction between the negative of the oxygen and the positive of the water, which is the H. That was worth 1 point to show this hydrogen bonding between the water and the formaldehyde. So as a review, how do we score this guy? We have 1 point for the structure in box X, 1 point for the structure in box Y, 1 point for saying box X was compound 2 and a reason, 1 point for stating box Y was compound 1 with a reason, a correct reason that is. We had 1 point and 1 point, 2 points for talking about the interactions between water and each one of these compounds. 1 point each, that's 2 points total, for talking about the interactions between the intermolecular forces between itself. And then we had one last point on the hydrogen bond attraction between the formaldehyde and the water. That's worth 9 points. So make sure you go to MrRating.com. Make sure you put in your score so I can know how you did. Any questions, make sure you let me know, and I'll catch you on the flip side.